A new chapter. We're on chapter 3 now. This is kinetics of particles, and in this section, we're going to look at work and energy. So in the last chapter, we did kinetics, but we looked at forces and accelerations. Now we're going to be looking at a different way to solve these problems. So we're going to derive the work and energy equations, and then in the next videos, we'll start doing examples. So let's start talking about work. And to start with this, let's go ahead and draw a picture. Now remember, we've got curved paths here, so let's draw a curved path. I've got some point O, and let's put a point 1 right here. So there's point 1. We're going to have a force that's applied here, just like that. And the force is applied, well, then we're going to be going to point 2. All right. So here is vector R going from O to the original point, and then at our new point, point 2, right, because if we're applying a force, we're going to have some motion here, we're going to have R plus, let's just call it dr. And this distance right here, let's just say is dr. Okay, so now we've got that. Now we want to find work. The equation for work, we're going to write down, u is going to be the variable. So we're going to have du equals F dotted with dr. All right, this is the main equation that we get for work. All right. All right, so now we've got this equation. Let's go ahead and let's kind of extend on this a little bit. So let's draw the force. Here's our force. Now the force is what's causing our particle to move from here to here. Okay, so we've got our force vector drawn. Now this is a curvilinear path, right? It's got curvature to it. So let's draw our N and T axes. All right, so here's N, and then we're going to have T like that. Okay. Now, if that's the case, we can get the components of F along the N and the T axes. Okay, so this one right here is going to be Fn, and we could write that as F sine of alpha. You're probably wondering what alpha is. Well, let me tell you. So alpha is going to be the angle between this T line, tangential line, and then the horizontal. All right, so let's draw this. There's alpha. All right, so if that is alpha, you could work your way around, and this right here would be alpha. Okay, so you get F sine alpha. Now, let's go ahead and keep going through this. Now, this component right here is going to be the tangential component. So this will be Ft. So this is going to be F cosine alpha. Again, because this is going to be alpha. Okay? So now we've got that. Now that we have that, let's go ahead and add one more thing. If this displacement right here, this line right here, if we use that to represent this dr, let's call this ds. So ds will be the magnitude of dr. If that's the case, if this is that length, I can use this angle to get this right here. So this would represent ds cosine alpha. All right, so all we did, we found this length, did the cosine to get this in the x direction. All right, now if you notice, F and this are along the same line, right? Those are along the same line. Now, let's look at each of the force components. So let's start with the tangential component. So if I take this tangential component and I dot that with ds, So if I do Ft dotted with ds, then that is going to give me du. All right, because look up here, we've got the work equals a force dotted with some distance. Okay, so we've got du here. Now, if I plug in my equation for Ft, I'm going to have du equals F cosine alpha, which is from right here, times ds. Okay, and I know that because if you think about these being vectors, right, because you could write these as vectors, these are along the same line, right? So the unit vectors here would be the same. So actually we could put these as vectors. So now if we do that, we're going to end up with this. Okay, so du is going to be F times ds cosine alpha. Now, if you look at that, we got F, and then we got ds cosine alpha right here. Okay, so now with that in mind, let's extend that, and let's look at Fn. So Fn dotted with dr, what's that going to be? Well, look right here. Here's Fn. Here was our ds, or our magnitude of dr. These are perpendicular, right? So this has to be 0. All right. So that's because our normal component is perpendicular to dr. So with that in mind, that means that our work, which remember u is work, our work is going to be the force, that's what you see right here, times the displacement in the direction of the applied force. And we can see that looking right here. All right. So notice, if y'all remember, I pointed out that F and ds cosine alpha are on the same line. Okay, so we've got our force, which is what we have here, times the displacement in the direction of the applied force. So this ds cosine alpha, that is the displacement in the direction of the force vector. All right, so that's what work is. So you're not going to have any work unless you have displacement in the same direction as your force. All right, so that's the only way you can have work. Now, we need to look at our sign convention. Actually, here's that written down again. So for the sign convention, we're going to have positive work if F is in the direction of dr, and then it's going to be negative if the force, it's an F there, is opposite the direction of dr. Okay, so that'll be our sign notation. But the important thing to note here, again, is you've got to have this displacement in the direction of the applied force. All right, so if you don't really understand all of this, don't worry about it too much. Just know that you got to have the force, and then you got to have a displacement in that same direction. Okay, otherwise there's no work being done. Okay. All right, so there's that. Now, let's look at springs. So for springs, let's go ahead and let's draw out a little picture. So there's my spring. Y'all know I can't draw. And then we've got a mass right here. So this is the unstretched length. And let's measure X from that line right there. Now, if I were to go and stretch this out, so let's say I apply a force to the mass and I pull it to the left, well, that's going to stretch the spring out, right? So that's stretched out. And if I draw a free body diagram, I've got P, and then the spring force always goes in the opposite direction. So we're going to have F, and then F is going to be K times X. So every time you see a spring, the force due to the spring is K times X. And it's always in the opposite direction of motion, right? Because a spring doesn't want to be stretched out, so it tries to go back to its natural unstretched length. So that's what we get when it's stretched. The other case would be if it's compressed. So P would be pushing to the right, and then the spring gets shorter. All right, now in this case, if we draw the diagram, we've got P. Now we're compressing the spring. Well, that spring doesn't want to be compressed. It wants to be at this length. So it's going to push back on the mass. So we're going to have a spring force going to the left, and that's going to equal K times X. And the X value is the amount of stretch or compression in the spring. Okay, it is not the length of the spring. It's the amount of compression or stretch. All right, so now we got that. And remember, just as a note here, the spring force is going to be opposite the direction of displacement. Okay, so since it's opposite, if we look at our work equation, U, which U is work, is going to be negative times the integral of du. All right. And remember, du was a force dotted with a dr. So in our examples here, everything is in x. So I'm going to say u equals negative times the integral x1 to x2 of f times dx. All right, so we got our force vector. We're dotting it with that displacement in the x direction. Now F is K times X. So that's going to give us negative 1 times the integral. And now we'll have Kx dx. Well, now if we integrate this, what we're going to get is u equals negative 1/2 K times x2 squared minus x1 squared. Right, so this is the equation for work done by a spring. Okay, and again, we know we have work because we've got a force and then we've got a displacement in the same direction as the force. Okay, so that's why we got work done here. Now let's just look at a general equation for force. All right, so if we've got a curved path again, let's look at a point. We've got t-axis, we've got n, and let's say we've got a force. So there's our force, and that's going to cause some displacement dr. So our equation for work is going to be u equals the integral of f dotted with dr. And f, we already know from previous sections, f is equal to ma. All right, so we're going to switch out f for ma. So we'll have the integral of mass times the acceleration vector dotted with dr. Notice those are both vectors because we're doing dot product. And then with this one, the only direction I care about is in the direction of the force. So I care about what's on this t-axis. All right. So that means for my acceleration, I only want the t acceleration. Okay, so I'm going to replace this up here with the integral of mass times the tangential acceleration times ds. All right, so this is what you'll get after you do the dot product. Okay, now what we're trying to do is we're going to get an equation for work that's a function of velocity. So let's focus in on this right here, this ATDS. Right, that's just a dot there. I didn't mean to draw that. Now remember, ATDS is equal to VdV, right? So let's go ahead and solve for AT. So you get VdV over ds, like that. And now with that, we're going to plug this into this equation. So we're going to have the integral of m v dv, because the ds's are going to cancel out once you plug that in. So now you get that. And for our limits, we're using v here, so we're going to go from v1 to v2. And then once you integrate, you get that work is 1/2 times mass times v2 squared minus v1 squared. All right, so this is the work done by a force. All right. And one more thing we'll do before we switch videos. So next thing we want to talk about is kinetic energy. All right, so let's talk about kinetic energy. Kinetic energy, what that is, that's just the total work. All right, so we got work here that's required to bring a particle from rest to some velocity v. That's all it is. Okay, so if I'm going from rest to a velocity v, I'm going to say t. T is my symbol for kinetic energy. T is going to be 1/2 mv squared. All right. So notice this is always going to be positive because this is squared. And work then will be delta t. All right. So if T is my kinetic energy, then I'm going to say that my change in kinetic energy is equal to work. All right, so U is going to be T2 minus T1. Okay. So now we've got that. And then last couple of things. So power is just the time rate of doing work. So the equation is P stands for power equals F dotted with V. Okay. The units for this will be watts. Watts are joules per second. And then in the English system, you'll have horsepower. Right, so horsepower is foot-pound per second. Right, so those are going to be your units. So that's all power is. It's just you're going to have F dotted with V. Okay, and finally, how do you know when to use this? You're going to use work energy when you want to relate displacement with some velocity change. Right, that's when you're going to want to use this. Okay, and the steps we're going to use, we're going to identify forces that do work. We'll know if they do work if we have a displacement in the direction of the force. Okay, we always draw the free body diagram, and then we're going to use our work energy equations. All right. So we will pick up our first example in the next video, guys. See y'all then.